When we look up at the starry night sky, space appears as a calm, inviting expanse, a quiet ocean of distant suns waiting to be crossed by human ingenuity. Popular science fiction has taught us to view interstellar travel as a mere question of propulsion engine power, build a larger fusion rocket, engage a warp drive, or enter a deep cryo-sleep pod, and humanity will wake up orbiting a star in the next system. But when we strip away the cinematic fiction and calculate the hard physical realities of traveling across deep space, a far more formidable, unyielding truth emerges. Crossing even a single light year is not simply a long journey across empty space. It is a violent thermodynamic trial that tests every physical law, every structural material, every chemical cycle, and every biological cell to its absolute breaking point. If you find value in these calm, deep explorations of space and the hidden mechanics of our universe, please consider subscribing and liking the video. Your support helps bring more thoughtful, scientifically precise documentaries to this channel. To grasp the staggering magnitude of a 1 light-year crossing, we must first dismantle the human entry intuition of distance. On Earth, human spatial comprehension is calibrated to terrestrial horizons, a scale where 1,000 kilometers represents a vast journey across continents. Even within our local planetary neighborhood, distances like the 384,000 kilometers to the Moon or the 54 million kilometers to Mars can still be mapped against chemical rocket burn times, measured in days or months. But 1 light-year equivalent to 9.46 trillion kilometers, or 63,241 astronomical units AU, represents an entirely different physical order of magnitude. It is a spatial expanse so immense that solar radiation, traveling at the absolute cosmic speed limit of 300,000 kilometers per second, requires 365 full days just to cross it. When we map this distance against human spaceflight history, the sheer scale becomes sobering. The Voyager 1 probe, launched in 1977 and currently the fastest outward-bound human artifact in existence, cruises through space at roughly 17 kilometers per second relative to the Sun. At this speed fast enough to cross the continental United States in under 4 minutes, Voyager 1 covers approximately 3.5 astronomical units per year. To cover a single light year, Voyager 1 would need to travel continuously for more than 17,700 years. If we launched a spacecraft at the dawn of human agricultural civilization 10,000 years ago at current probe speeds, it would today be barely past the halfway mark of a single light year. Furthermore, the physical structure of a 1 light-year journey crosses 3 distinct astronomical zones, each presenting unique physical boundary dynamics. The first zone extends from low Earth orbit out to Neptune at 30 AU, a region dominated by the Sun's immense gravitational well and dense planetary orbits. The second zone spans the Kuiper Belt and the scattered disk from 30 to 1,000 AU, populated by trillions of icy planetesimals and volatile cometary bodies. The third and largest zone is the inner Oort cloud, extending from 1,000 out to past 60,000 AU. In this vast, freezing domain, the Sun's gravitational pull decays to a tiny fraction of its terrestrial value, leaving icy bodies weakly bound by galactic tidal forces. Crossing 1 light-year is not simply traversing empty void, it is navigating through the primordial gravitational debris field left over from the formation of the solar system. This extreme spatial scale introduces severe relativistic light travel delay penalties that permanently isolate the traveller from Earth's real-time communications. At a distance of half a light-year, a radio signal transmitted from the ship takes 6 full months to reach Earth, and a reply takes another 6 months to return. By the time the vessel reaches the 1 light-year mark, a full 2-year communication latency loop separates the crew from Earth. Real-time telemetry monitoring, remote mission assistance, and interactive guidance from ground control become physically impossible. the spacecraft must operate as an entirely autonomous computational island, making real-time life-or-death decisions without external oversight. In addition to communications latency, gravitational perturbation dynamics across light years alter the vessel's navigation trajectory. As the ship leaves the deep gravity well of the Sun, the gravitational pull of the galactic core, neighboring star systems like Alpha Centauri and dark matter halos in the Milky Way disk exert competing microgravitational accelerations. Even a micro-arc second deviation in guidance trajectory accumulated over 63,000 AU results in missing a target planetary system by billions of kilometers, requiring continuous, power-intensive mid-course navigation burns. Moreover, the sheer volume of space-crossed introduces severe statistical probabilities of encountering unmapped icy planetesimals. In the inner Oort cloud, numerical simulations indicate millions of low-albedo cometary nuclei, ranging from meters to kilometers in diameter. Because these objects reflect almost no sunlight and emit virtually no thermal infrared radiation, bow radar systems operating on onboard power grids struggle to detect them beyond a few astronomical units ahead. Navigating a 1 light-year corridor requires constant active sensor sweeping, consuming precious energy and requiring rapid, automated thruster corrections to prevent catastrophic collisions. Furthermore, light travel time delay severely disrupts real-time scientific telemetry analysis. At half a light-year out, if an onboard diagnostic sensor records an anomalous plasma frequency peak or a microleak in primary coolant loops, human flight controllers on Earth will not learn of the anomaly for 6 months. Any advice or software patch transmitted from Earth will take another 6 months to arrive, by which time a full year of shipboard operational time has elapsed. The crew is utterly alone, governing a self-contained nuclear ecosystem across a temporal abyss. Finally, the scale paradox manifests as a profound psychological realization for the crew. Looking back toward the inner solar system at a distance of 60,000 astronomical units, the Sun is no longer a blazing golden disk. It has shrunk to a bright pinpoint star among thousands of others in the constellation Cassiopeia. Earth and all its planets have faded completely out of optical visibility. The traveler is suspended in an absolute black void, detached from the planetary cradle that birthed their species, with no visual landmark to anchor their sense of origin. To put this spatial scale in thermodynamic perspective, consider the total kinetic energy required to bridge 63,000 astronomical units. Accelerating a multi-thousand-ton habitat up to 2% of light speed consumes more energy than the total annual energy production of human civilization on Earth. Every meter of progress through the Oort cloud demands continuous thermodynamic expenditures that drain nuclear fuel reserves. The scale paradox is not merely a geometric challenge, it is an unyielding energy boundary that dictates the structural lifespan of the vessel. Moreover, navigation instruments face severe frame-of-reference shifts. On Earth and in LEO, spacecraft determine orientation using star trackers locked onto bright reference stars like Canopus or Sirius. Over a 1 light-year displacement, stellar parallax causes nearby reference stars to shift position against background galaxies. The familiar optical geometric grid used for spacecraft navigation alters continuously, forcing navigation software to recalculate autonomous astrometric baselines every light month. Furthermore, the density gradient of interstellar dust changes across a 1 light-year distance. As the vessel transitions from the solar wind cavity into the local interstellar cloud, dust density increases by several orders of magnitude. The ship moves from a relatively benign planetary vacuum into an active interstellar gas cloud, where particle encounter rates surge dramatically. This gradient shift forces the habitat to adjust its kinetic shielding and radiation rejection protocols continuously as it penetrates deeper into the interstellar medium. Ultimately, the scale of 1 light-year humbles human technological hubris. It demands that an artificial habitat survive without resupply, maintenance, or external energy for timescales longer than entire human historical empires. The vessel must be capable of executing millions of autonomous self-repair cycles, processing billions of cubic meters of atmosphere, and maintaining structural integrity across quadrillions of kilometers of deep space. It is a distance that transforms spaceflight from a mechanical journey into a multi-generational survival test. Furthermore, the physical geometry of navigating the inner Oort cloud requires a deep understanding of gravitational sphere of influence, SOI limits. The Sun's Hill sphere, the region where solar gravity dominates over galactic tides, extends out to roughly 100,000 astronomical units, about 1.5 light years. Near the edge of this Hill sphere, galactic gravitational torque from the Milky Way disk and perturbations from passing giant molecular clouds, GMCs induce long-term orbital precession on the spacecraft's trajectory. Because these external galactic forces act continuously over decades, guidance navigation systems cannot rely on simple Keplerian orbital mechanics. Autonomous flight software must run real-time n-body numerical integrators, incorporating galactic potential models to compute precise mid-course trajectory corrections. Even minor computational rounding errors in trajectory prediction algorithms can cause the ship to drift into high-density cometary swarms or miss the gravitational capture corridor of the target star system entirely. Moreover, optical telemetry transmission across 63,000 astronomical units presents monumental engineering challenges. To transmit diagnostic data back to Earth from a distance of 1 light year, the vessel must deploy high-power laser communication arrays operating at near-infrared wavelengths. To achieve readable signal-to-noise ratios over light-year distances, the ship's laser transmitter must maintain pointing jitter below a few nanoradians while mounted on a rotating habitat hull that is experiencing micro-vibrations from internal machinery. If pointing control degrades by even a fraction of a microarc second, the focused laser beam misses Earth by millions of kilometers, severing the ship's final data link with human civilization. The traveler becomes completely blind to news from home, while Earth receives only silent space where a thriving starship once beamed its telemetry. This permanent loss of optical contact marks the true end of the human tether to the solar system. Beyond the planetary boundary of the solar system lies the first major invisible frontier of interstellar space, the heliopause. On Earth, we live protected inside a vast plasma bubble carved out by the solar wind, a supersonic stream of charged particles, mostly protons and electrons, ejected continuously from the sun's corona at speeds of 300 to 800 kilometers per second. This solar wind expands outward across the solar system, carrying with it the interplanetary magnetic field IMF and creating the heliosphere, a protective magneto-hydrodynamic shield spanning over 100 astronomical units in radius. As a spacecraft travels outward toward the 1 light-year mark, it must cross the termination shock, the boundary roughly 80 to 100 AU from the Sun, where the supersonic solar wind abruptly drops below the local speed of sound as it rams into the ambient interstellar medium. Crossing the termination shock induces severe plasma turbulence and high-frequency magnetic fluctuations. Passing through this boundary, spacecraft instruments record a sharp increase in plasma density, a sudden rise in magnetic field intensity, and a rapid thermalization of solar ions. Beyond the termination shock lies the heliosheath, a turbulent transition zone leading directly to the heliopause, the sharp thermodynamic boundary where the outward ram pressure of the solar wind balances the inward pressure of the interstellar medium. Beyond the heliopause, the protective magnetic umbrella of the Sun vanishes entirely. The spacecraft enters the local interstellar cloud Lycae, a cold, partially ionized gas environment composed of neutral hydrogen and helium atoms, interstellar dust grains, and raw galactic cosmic rays GCRs. Exiting the heliosphere exposes the vessel to a sharp spike in low-energy cosmic particles and interstellar magnetic field interactions. Inside the heliosphere, the solar wind sweeps away a large fraction of galactic cosmic particles below 1 giga-electronvolt. But in interstellar space beyond the heliopause, the ambient cosmic particle flux surges by over 300%. The spacecraft transitions from a solar-dominated magnetic regime into an unattenuated interstellar plasma environment, subjecting hull materials and human occupants to unshielded galactic particle bombardment. Furthermore, crossing the heliopause triggers severe hull charging dynamics. As the vessel transitions from the warm, low-density solar wind plasma into the cold, dense interstellar cloud medium, differential photoemission and electron collection cause high-voltage electrostatic charges to accumulate across non-conductive composite hull surfaces. Electric field gradients exceeding thousands of volts per meter develop between shielded structural bulkheads and exposed sensor arrays, risking catastrophic electrostatic discharge (ESD) events that can fry sensitive front-end electronics and trigger control bus short circuits. In addition, interaction with interstellar magnetic fields creates continuous inductive drag against the spacecraft's hull. The local interstellar cloud possesses an ambient magnetic field oriented at an angle to the ship's heading. As a conductive metal vessel cruises through this interstellar magnetic field at relativistic speeds, motional electric fields induced by movement across magnetic fields induce eddy currents in structural bulkheads. These eddy currents generate opposition magnetic fields that act as a subtle but relentless particle brake, draining kinetic energy and generating waste heat in the structural frame. Moreover, the transition across the heliosheath exposes hull materials to severe ambient neutral hydrogen atom bombardment. Neutral interstellar hydrogen atoms are undeflected by magnetic shields. Traveling at relativistic relative speeds, these gas atoms penetrate deep into outer protective layers, causing localized atomic displacement and ion implantation that blunts optical lenses and degrades thermal emissivity coatings on radiator panels. Finally, the boundary dynamics of the heliopause exhibit significant temporal variability driven by solar activity cycles. During solar maximum, high-speed coronal mass ejections expand the heliosphere outward, pushing the heliopause boundary further into interstellar space. During solar minimum, the boundary contracts inward. A spacecraft navigating this transition encounters oscillating shock fronts and turbulent magnetic reconnections, subjecting the ship's outer structure to complex, fluctuating electromagnetic forces. To analyze the magneto-hydrodynamic interaction in detail, the heliopause acts as an astrophysical bow shock. The interstellar medium, moving at roughly 26 kilometers per second relative to the Sun, creates a magnetic barrier where interstellar magnetic field lines drape around the heliosphere. As the spacecraft pierces this magnetic wall, external magnetic pressure surges, inducing magnetic reconnection events along the vessel's hull. These reconnections accelerate local ions, creating localized bursts of high-energy X-ray radiation. Additionally, neutral hydrogen atoms crossing the heliopause undergo charge exchange reactions with solar wind protons, creating a high-density hydrogen wall ahead of the heliopause. This hydrogen wall absorbs specific ultraviolet wavelengths, creating a dense neutral gas barrier that the vessel must plow through. Collisions with this neutral hydrogen accumulation increase bow drag and generate secondary ultraviolet fluorescence that bathes the forward hull. Furthermore, plasma wave instabilities along the heliopause transition boundaries such as Kelvin-Helmholtz and Rayleigh-Taylor instabilities create turbulent plasma vortices. These vortices induce rapid, unpredictable fluctuations in plasma density around the vessel. Automated control systems must continuously adjust magnetic shielding frequencies to prevent plasma resonance from coupling with onboard electrical power networks. Exiting the heliosphere represents a point of no return. The vessel leaves behind the protective solar cocoon that nurtured Earth's biological history, entering the raw, unshielded galactic environment. The environment beyond the heliopause is not simply colder and darker, It is electromagnetically hostile, demanding that the spacecraft serve as its own magnetosphere for the remaining 99% of the 1 light-year journey. To examine the plasma physics of the heliopause transition in greater detail, we must consider the dynamics of magnetic wall formation and pick-up ion thermalization. As solar wind protons stream outward, they collide with interstellar neutral hydrogen atoms through charge exchange reactions. The energetic solar protons capture electrons from cold interstellar hydrogen, transforming into fast neutral hydrogen atoms that escape the solar system, while the cold interstellar hydrogen atoms become slow pick-up ions, trapped by the interplanetary magnetic field. These pick-up ions absorb a massive fraction of the kinetic energy of the solar wind, heating the heliosheath plasma to millions of degrees Kelvin. When a spacecraft penetrates this heated pick-up ion shell, outer structural materials absorb high fluxes of low-energy thermal ions that cause surface blistering and sputtering on thermal control coatings. The vessel must navigate through a boiling plasma shock layer before emerging into the cold, dense interstellar cloud beyond. Furthermore, interstellar magnetic field alignment creates asymmetric plasma pressure gradients across the vessel's hull. The local interstellar cloud magnetic field is inclined relative to the ecliptic plane, causing interstellar plasma to flow around the heliopause in an asymmetric magnetic sheath. As the ship crosses this inclined magnetic boundary, structural bulkheads experience asymmetric Lorentz forces induced by movement across magnetic fields that induce microstructural shear stress across long structural girders. This magnetic shear stress, while subtle compared to main engine thrust, acts continuously for years during the boundary transit. Structural welds experience cyclic electromagnetic flexing as the vessel rolls, accelerating fatigue crack growth along metallic seams. Piercing the boundary of the solar system is thus an active magneto-hydrodynamic ordeal that tests the electromagnetic resilience of every structural joint on board. In addition to magnetic draping and pick-up ion thermalization, exiting the heliosphere exposes the vessel to the full flux of low-energy cosmic rays previously modulated by solar activity. On Earth, solar magnetic sector boundaries and coronal mass ejections, CMEs, generate the four-bush decrease effect, a temporary drop in galactic cosmic ray intensity, caused by solar plasma clouds sweeping away cosmic particles. Out in the interstellar cloud beyond the heliopause, solar modulation drops to zero. Without four-bush decreases or solar magnetic shielding, the baseline cosmic radiation flux remains continuously high. Low-energy cosmic rays below 100 mega-electron-volts, which are completely blocked inside the solar system by the heliospheric magnetic boundary, strike the spacecraft's outer hull without pause. These lower-energy cosmic ions, while possessing less penetration depth than relativistic heavy ions, deposit their kinetic energy extremely rapidly inside outer hull layers, accelerating surface sputtering, radiolytic degradation of thermal insulation, and surface ionization. Furthermore, the physical geometry of the heliopause creates a vast interstellar shock structure known as the astrospheric bow wave. As the Sun moves through the local interstellar cloud at 26 kilometers per second, it compresses ambient interstellar magnetic fields and neutral hydrogen gas ahead of its path. A spacecraft departing toward the bow wave direction must plow through an elevated density of interstellar gas and compressed magnetic fields, experiencing higher kinetic friction and stronger inductive drag than a ship departing in the trailing heliotail direction. To cross a 1 light-year gulf within a human lifespan, say, 50 years, a spacecraft must achieve an average cruise velocity of at least 2% of the speed of light, or roughly 6,000 kilometers per second. At these extreme interstellar velocities, the thin, seemingly empty void of space transforms into a lethal kinetic firing range. According to classical and relativistic kinetic energy equations, the impact energy released by a colliding particle scales quadratically with velocity. At 2% of light speed, striking even microscopic dust grains becomes an explosive kinetic event. The interstellar medium contains an average dust density of 1 microgram per cubic kilometre, consisting of silicate grains, carbonaceous polycyclic aromatic hydrocarbons pH, iron microparticles, and water ice grains ranging from sub-micron sizes up to a few millimeters. When a spacecraft travelling at 6,000 kilometers per second collides with a tiny 1 milligram dust grain, the impact releases kinetic energy equivalent to the detonation of nearly 20 kilograms of high explosive TNT. Upon impact, the kinetic energy density is so immense that both the dust grain and the target armor material instantaneously hypervaporize, forming an ultra-high temperature plasma flash that blasts deep, crater-like microcavities into the forward hull shielding. To survive this relentless kinetic bombardment across a 1 light-year trajectory, the vessel must deploy sacrificial forward Whipple shields, tungsten bumper plates, or thick sacrificial ice shields spanning tens of meters ahead of the habitat module. However, continuous hypervelocity impacts cause severe forward shield ablation, grinding away meters of protective material over decades of flight. Furthermore, high-velocity collisions between ambient neutral hydrogen gas atoms and the forward shield generate nuclear sputtering, producing an intense flux of hard secondary X-rays and gamma-ray Bremsstrahlung radiation that shines directly backward into the living quarters. Beyond dust impacts, the risk of colliding with larger millimeter or centimeter-sized micrometeorites in the inner Oort cloud poses a catastrophic threat. At 2% of light speed, a collision with a 1-gram ice fragment releases energy equivalent to 20 tons of TNT, instantly vaporizing primary forward shielding and blasting relativistic plasma shock waves through the structural frame. The kinetic energy required to push a vessel through a 1 light-year dust corridor imposes a non-negotiable structural mass tax, forcing mission planners to devote more than half of the ship's initial weight to kinetic shielding alone. Additionally, hypervelocity impacts generate intense localized electromagnetic pulses, EMP, as kinetic impacts vaporize bow armor into expanding plasma clouds. Rapid separation of positive ions and free electrons induces high-voltage electrical surges in unshielded sensors, optical cameras, and automated repair arrays mounted on the forward hull. Repeated EMP bombardment burns out sensitive front-end electronics over decades of cruising through interstellar dust lanes. Moreover, relativistic plasma shock waves generated by bow impacts propagate backward along the structural length of the vessel. As forward armor plates absorb hypervelocity collisions, shock waves travel through load-bearing girders at the speed of sound in metal. These acoustic shock waves induce micro-vibrations and high-frequency cyclic fatigue in structural welds hundreds of meters behind the shield, accelerating metal fatigue in internal pressure bulkheads that never directly touch interstellar dust. Furthermore, continuous microscopic cratering causes severe degradation of thermal rejection surfaces on forward-facing radiator components. Microejector blasted from impact craters sprays backward across the hull, coating thermal emissivity panels with microscopic metal dust. This contamination reduces radiative cooling efficiency, causing waste heat to back up into primary power distribution buses. Finally, the momentum transfer from continuous particle impacts imposes an unrelenting kinetic deceleration force on the vessel. Striking trillions of gas atoms and dust grains per second acts as an interstellar drag brake, bleeding off forward momentum and requiring continuous thruster pulses to maintain target velocity across the light-year expanse. To examine the physics of hypervelocity impacts, consider the hydrocode mechanics of hypervelocity cratering. When an interstellar dust grain strikes the bow at 6,000 kilometers per second, the impact velocity far exceeds the speed of sound in any known solid material. The resulting pressure wave generates shock stresses measured in terapascals, completely exceeding the atomic shear strength of tungsten, titanium, or diamond-like carbon armors. The target material behaves not as a solid metal, but as a compressible fluid undergoing instantaneous hydrodynamic expansion. This hydro-expansion creates parabolic impact craters surrounded by microfracture zones. Repeated impacts overlap, creating a spongy, micro-cratered surface layer that drastically increases surface area. This expanded surface area absorbs subsequent impacts less efficiently, leading to non-linear ablation acceleration where shield thickness bleeds away at exponentially increasing rates over time. Additionally, sputtering caused by relativistic gas collisions operates at the atomic level. Incoming neutral hydrogen protons with energies of several kilo-electron-volts knock target metal atoms out of their crystal lattice through direct nuclear recoil. This physical sputtering systematically strips atom after atom from the forward surface, eroding high-density armor plates even in regions completely free of solid dust grains. The speed penalty proves that velocity in deep space is not free. Pushing a vessel faster to shorten trip time exponentially increases kinetic ablation, secondary radiation production, and structural shock fatigue. The ship is trapped in a brutal physical trade-off: travel slowly and succumb to multi-generational life support decay, or travel quickly and face catastrophic kinetic destruction from the interstellar medium itself. To understand the full scope of kinetic damage at 2% of light speed, we must analyze the physics of secondary radiation cascades produced within bow armor when a relativistic dust grain or gas atom strikes a forward whip shield. Hypervelocity impact shockwaves generate intense bremsstrahlung X-rays and high-energy secondary neutrons. These secondary particles pass straight through outer tungsten bumper plates, penetrating deep into interior structural bulkheads and habitat modules. This secondary radiation environment creates a severe biohazard for crew members living behind the forward shield. Even if the outer kinetic armor successfully absorbs the physical impact energy of dust grains, the resulting X-ray and neutron flash bathes forward crew decks in ionizing radiation. Engineers must construct heavy liquid water or polyethylene secondary radiation bulkheads behind the kinetic shield, adding thousands of tons of passive mass that further increases initial launch propellant requirements. Furthermore, hypervelocity dust impacts cause severe surface cratering on forward optical windows, navigation sensors, and optical communication mirrors. Over decades of cruising through interstellar space, continuous micro-cratering transforms smooth, transparent quartz viewports into opaque, frosty surfaces that scatter optical light. Front-end cameras and stellar tracking sensors lose optical resolution, rendering automated star tracking navigation increasingly inaccurate. To mitigate sensor degradation, automated maintenance systems must continuously deploy sacrificial polymer film covers over forward sensor lenses, discarding pitted covers as they degrade. However, carrying thousands of replacement optical films adds cargo weight, and mechanical film deployment mechanisms operating in absolute vacuum are vulnerable to mechanical binding and cold welding. The forward eye of the starship steadily dims as it pushes through the interstellar dust lane. To further evaluate hypervelocity impact mechanics, we must consider the phenomenon of explosive plasma flash expansion and secondary impact sputtering. When a dust particle vaporizes upon impact with tungsten armor, the resulting high-density plasma cloud expands at speeds exceeding 20 kilometers per second. This expanding plasma cloud exerts intense outward gas dynamic pressure against the rim of the impact crater, peeling back metal lips and flinging molten microdroplets backward into space. These molten microdroplets, moving at high velocity relative to the ship, collide with adjacent forward structures, creating a secondary cratering halo around primary impact sites. Over decades of cruising, secondary microdroplet impact halos overlap, transforming smooth structural plates into rough, microfragmented surfaces with severely compromised structural integrity. Moreover, relativistic dust impacts generate high-frequency acoustic emissions that excite structural resonance modes inside load-bearing girders. Acoustic stress waves propagating through titanium hull frames reflect off internal bulkheads, creating standing wave interference patterns. Where destructive acoustic interference occurs, localized stress concentrations spike, driving microcrack propagation along internal weld lines and mechanical joints far removed from the forward shield. Furthermore, the physical dynamics of kinetic impact energy absorption at relativistic speeds demand an evaluation of nonlinear shockwave reflection inside composite armors. When a hypervelocity dust grain impacts a multi-layered Whipple shield, the primary shockwave reflects off density interfaces between tungsten bumper plates and carbon composite backing matrices. This shockwave reflection creates intense local tensile stress spikes that cause spallation fractures along internal material interfaces, causing structural layers to delaminate long before physical impact craters penetrate the full shield thickness. To prevent delamination failure, engineers must incorporate viscoelastic energy dissipation layers that absorb acoustic shock frequencies. However, these organic dampening polymers undergo radiolytic cross-linking and outgassing under continuous cosmic ray exposure. Losing their shock-absorbing capacity after a few decades of cruise flight, the forward shield steadily loses its structural resilience, leaving the habitat vulnerable to progressive kinetic degradation. As a spacecraft accelerates to significant fractions of the speed of light across a 1 light-year journey, the very act of looking out the window reveals a strange, counterintuitive visual transformation dictated by Einstein's theory of special relativity. Human visual perception is accustomed to fixed spatial geometries, where looking forward while traveling displays stars remaining in their fixed constellations. But at relativistic cruise velocities such as 10 to 20% of the speed of light, the visual sky ahead undergoes severe relativistic aberration, Doppler shifts, and searchlight concentration. Relativistic aberration is caused by the finite speed of light combined with the high forward velocity of the observer. As the ship speeds through interstellar space, light rays arriving from stars located to the sides and even slightly behind the vessel are swept forward into the direction of motion. To the crew inside, the entire visible sphere of stars appears to collapse, forward into a narrowing, bright optical cone centered directly on the ship's heading. Constellations ahead compress into hyper-dense star clusters, while stars behind the vessel drift out of view, creating a growing visual void in the rear hemisphere. Simultaneously, the relativistic Doppler effect dramatically alters the color and energy spectrum of incoming starlight. Photons arriving from stars in the forward cone of motion are blue shifted to higher frequencies and shorter wavelength. Visible optical light from target stars shifts into the ultraviolet, X-ray, and hard gamma-ray spectrum, rendering stars invisible to the naked human eye while bombarding the bow with ionizing radiation. Conversely, starlight behind the vessel is red-shifted down into the infrared and microwave spectrum, fading into invisibility. Furthermore, the cosmic microwave background CMB, the ambient 2.7 Kelvin thermal radiation bathing the universe, undergoes extreme relativistic Doppler boosting ahead of the vessel. At relativistic speeds, the cold microwave photons of the CMB are shifted up into the visible optical light spectrum, transforming the seemingly dark void ahead into a glowing, brilliant optical headlight. The traveler does not gaze out into a dark, familiar starry night. They look out through a distorted relativistic lens where stars shift into invisible gamma rays, while the cold background of space glows with intense optical light. Moreover, optical navigation systems experience severe distortion under relativistic aberration. Stellar tracking sensors engineered to calculate space coordinates based on fixed constellation geometries fail as stars shift position relative to velocity vectors. Automated flight software must constantly compute Lorentz transformation matrices to correct optical star maps, preventing guidance system drift during relativistic cruise. Additionally, the concentration of forward photon intensity, known as the relativistic searchlight effect, creates intense radiation pressure against the forward shield. Although small compared to kinetic dust impacts, high-frequency blue-shifted photons exert continuous radiation drag, requiring additional propulsive energy to maintain cruise velocity over light-year distances. Furthermore, visual blue shifting converts ambient ultraviolet starlight into hard ionization X-rays. Windows and optical viewports constructed of high-purity quartz or sapphire experience radiolytic darkening, turning brown and opaque under continuous high-energy photon bombardment. Human eyes looking out forward-facing ports would suffer acute retinal burns from blue-shifted starlight that has been compressed into energetic radiation beams. Finally, relativistic light distortion creates intense psychological disorientation for the human crew. Human spatial cognition relies on stable visual reference points. Looking out into a sky where constellations collapse into bright forward halos while rear space turns completely pitch black disrupts deep spatial orientation mechanisms in the brain, inducing chronic motion confusion and visual hallucinations. To calculate relativistic aberration mathematically, the angle of an incoming photon in the observer's frame is related to the angle in the resting frame by the Lorentz transformation equation governed by special relativity, where psi theta c at 20% of light speed psi theta is to 0.2, a star located at a 90-degree right angle to the ship's trajectory appears displaced forward by nearly 12 degrees. As velocity increases, this compression accelerates nonlinearly. Furthermore, a spectral flux amplification follows the relativistic Doppler effect. In the forward direction of motion, photon energy is blue-shifted into significantly higher frequency bands. At relativistic speeds, infrared radiation emitted by cool red dwarf stars ahead is blue-shifted into intense blue visible light, while yellow sun-like stars transform into violet and ultraviolet radiation sources. This optical transformation alters astronomical observation abilities on board. Astronomical telescopes mounted on the ship cannot perform standard imaging of target planetary systems during cruise. Spectral lines used to identify planetary atmospheres are Doppler-shifted far outside design receiver bands, requiring active computational deconvolution to reconstruct true planetary spectra. The relativistic lens reminds the traveller that high-speed spaceflight fundamentally distorts human perception of reality. The universe viewed at relativistic speeds is not the static, peaceful cosmos seen from Earth's surface. It is an optically warped, Doppler-shifted environment where light itself becomes an energetic hazard. To examine relativistic optical transformations in greater detail, we must examine the phenomenon of spectral energy concentration and visual field distortion. As velocity increases towards significant fractions of light speed, the total radiant flux received from the forward hemisphere scales with the fourth power of the Doppler factor, F, total propto d4. This extreme flux concentration means that the forward bow of the spacecraft is illuminated by an intensely bright, highly focused beam of blue-shifted radiation. This intense forward radiation flux creates severe thermal heating on forward-facing hull surfaces. Infrared starlight from target stars, blue-shifted into the ultraviolet and optical spectrum, deposits gigawatts of energy onto forward radiator panels and shield plates. Thermal control systems must continuously pump heat away from the bow to the shaded rear of the vessel to prevent localized structural overheating during relativistic cruise. Furthermore, relativistic visual distortion creates severe cognitive challenges for automated image processing algorithms. Computer vision arrays engineered to recognize target star systems or identify approaching Oort cloud planetesimals must continuously process complex geometric Lorentz transformations in real time. If an optical sensor fails to account for relativistic aberration, an approaching asteroid appears displaced from its true physical location, causing automated collision avoidance thrusters to fire in the wrong direction. The relativistic lens demonstrates that motion at cosmic speeds alters the fundamental relationship between observer and universe. The traveller does not observe space as it's resting. They inhabit a Doppler-shifted, aberration-warped visual reality created by their own extreme kinetic energy. To analyze relativistic optical phenomena in detail, we must also account for the relativistic polarization angle rotation of incoming starlight. As light rays pass through the Lorentz transformation from the resting frame to the moving observer's frame, the electric field vector of polarized starlight undergoes a spatial rotation angle that depends on relative velocity and arrival angle. For automated optical sensors relying on polarized light measurements to analyze interstellar dust properties or magnetic field orientations, this relativistic polarization rotation introduces systematic measurement errors. Automated astronomical arrays must continuously run real-time polarization transformation algorithms to reconstruct true interstellar magnetic field vectors. Furthermore, the intense concentration of blue-shifted photons ahead creates a phenomenon known as optical photon-photon scattering. At ultra-high relativistic speeds, incoming high-energy blue-shifted photons interact with ambient cosmic microwave background photons, creating localized electron-positron pair production cascades in front of the bow. Although rare at 2% of light speed, as velocities approach higher relativistic thresholds, this photon-photon pair production creates a dense electron-positron plasma sheath ahead of the ship, adding further particle drag and electromagnetic interference. Additionally, relativistic visual field compression alters the spatial perception of target solar systems during final approach phases. At 20% of light speed, a target star system positioned directly ahead appears visually displaced from its true physical location due to relativistic aberration. As the spacecraft begins its deceleration burn, its velocity vector decreases, causing stars in the forward cone of motion to gradually expand outward toward their resting constellation coordinates. This optical expansion effect, known as relativistic sky unfolding, requires automated optical navigation software to continuously update target tracking matrices during deceleration. If flight computers fail to adjust for velocity-dependent optical expansion, automated maneuvering thrusters fire along incorrect guidance vectors, wasting precious deceleration propellant during the most critical navigational phase of the light-year crossing. Furthermore, relativistic optical transformation alters the solar power collection geometry of auxiliary photovoltaic arrays during initial departure phases. At relativistic speeds, light rays from the sun behind the vessel undergo severe relativistic backward suppression, causing photon flux in the backward direction to drop significantly due to relativistic intensity dimming. This relativistic beam suppression means that solar panels facing backward receive exponentially less solar energy than predicted by classical inverse square radiation laws alone. Auxiliary solar power generation crashes almost instantly upon reaching relativistic cruise velocities, forcing the ship to rely entirely on internal nuclear fusion cores for all electrical power needs. Beyond optical distortions and kinetic hazards, a 1 light-year journey subjects the human body to a profound biomechanical crisis, managing gravity over decades of deep space transit. Human physiology is an evolutionary product of Earth's continuous 1G gravitational field. Our skeletal architecture, cardiovascular fluid pressures, muscle tone, vestibular orientation, and cellular transport mechanisms rely on a constant downward acceleration vector. In the absolute weightlessness of unpowered deep space crews, human biology degrades rapidly. Without gravity pulling fluids toward the lower extremities, cardiovascular fluid redistributes upward toward the chest and head. Fluid pressure inside the cranium surges, deforming the eye structure and optic nerve sheath, a condition known as spaceflight-associated neuroocular syndrome (SANS). SANS causes optic disc edema, globe flattening, and progressive irreversible visual impairment. Simultaneously, osteoclasts absorb bone mineral matrix at a rate of 1 to 2% per month, releasing calcium into the bloodstream and causing severe osteoporosis, kidney stones, and skeletal fragility. muscle mass rapidly atrophies, while heart muscle tissue shrinks due to reduced fluid pressure workload. To prevent human biological collapse over a multi-decade crossing, the spacecraft must manufacture artificial gravity via continuous rotation. By engineering the vessel as a spinning tethered habitat ring or rotating cylinder, centripetal acceleration simulates Earth gravity on outer deck floors. However, artificial gravity created by rotation introduces severe Coriolis cross-coupling dynamics. When a crew member moves their head or walks across a rotating deck, Coriolis forces act on fluid inside the inner ear semicircular canals, creating intense illusions of tumbling, severe vestibular disorientation, and motion sickness. Furthermore, rotating a giant starship creates massive structural fatigue. Rotary joint bearings connecting spinning habitat modules to non-spinning utility hubs undergo billions of stress cycles, suffering micropitting, galling, and tribological wear in space vacuum. Dynamic fluid movement inside water ballast tanks induces precession wobbling, generating cyclic bending moments across structural spokes. The crew is caught in an unyielding biomechanical paradox floating in zero gravity, causes physical breakdown within months, while spinning the ship to create artificial gravity actively destroys the mechanical integrity of the vessel over decades. Additionally, fluid structure interaction instabilities between spinning habitat rings and internal liquid storage tanks accelerate mechanical wear. Carrying thousands of tons of liquid water in spinning rings creates complex fluid sloshing dynamics. Shifting water masses in partially filled ballast tanks alter the center of gravity and principal moment of inertia, inducing gyroscopic wobbling that places asymmetric bending torques on central hub bearings and pressure seals. Moreover, mechanical fatigue and structural support spokes poses a catastrophic failure risk. As rotational speeds interact with machinery vibration frequencies, micro-oscillations propagate down structural girders. Over decades of rotation, these micro-oscillations induce standing harmonic waves that accelerate microcrack growth along load-bearing welds, threatening structural separation of habitat rings from central utility hubs. Furthermore, Coriolis forces severely disrupt internal fluid transport systems. Water pumped radially upward from outer habitat decks toward the zero-G hub experiences lateral Coriolis drag against pipe walls. Pumping actuators must expend up to 30% more power to overcome turbulent eddies, generating excess waste heat that burdens internal cooling loops. Finally, long-term artificial rotation disrupts microvascular fluid dynamics inside cellular membranes. Endothelial cells lining blood vessels experience altered shear stress profiles under rotational acceleration gradients. Over decades, this rotational vascular stress leads to chronic arterial stiffness, impaired capillary perfusion, and microvascular tissue ischemia in outer deck inhabitants. To analyze centripetal acceleration mechanics, the gravity gradient across human height in a rotating habitat must be considered. In a rotating cylinder of radius r, centripetal acceleration is AC, omega 2r. A person standing upright experiences a higher acceleration at their feet than at their head. In a habitat with a 50-meter radius, the gravity difference between head and feet exceeds 3%. This steep gravity gradient creates continuous vascular pressure imbalances between the head and lower torso, triggering chronic autonomic nervous system confusion. Furthermore, moving relative to the direction of rotation alters apparent weight. Walking in the direction of spin increases centripetal acceleration, making the crew member feel heavier. Walking counter to spin decreases apparent weight. Running across a rotating deck causes fluctuating weight changes that disrupt gait mechanics and joint alignment, leading to chronic knee and hip microtrauma across multi-decade flight times. Moreover, the mechanical seals on rotary slip joints represent critical single-point failure nodes. These rotary seals must maintain airtight pressure against absolute vacuum while transferring electrical power, fluid coolants, and data cables between spinning and non-spinning frames. Over billions of rotations, seal face polymers suffer microgalling and outgassing. Atmospheric leakage through rotary seals steadily bleeds habitat air into space, requiring constant pressure resupply from compressed nitrogen and oxygen reserves. The gravity paradox highlights the fundamental tension of interstellar bioengineering. Human biology cannot endure zero gravity, yet artificial rotation introduces severe mechanical wear, Coriolis disorientation, and structural resonance risks. Managing gravity across a 1 light-year journey requires constant engineering vigilance, balancing human health against mechanical fatigue. To analyze the long-term biological consequences of artificial rotation gravity, we must examine cellular mechanotransduction dynamics in human tissue. Human cells sense gravity through specialized mechanoreceptors, focal adhesions, and cytoskeletal filaments. Under constant Earth gravity, cellular cytoskeletons maintain structural tension that regulates gene expression, protein synthesis, and cell division. In a rotating habitat with steep gravity gradients and Coriolis forces, cellular mechanoreceptors receive fluctuating, directionally unstable force vectors. Endothelial cells lining blood vessels and osteocytes inside bone tissue experience altered mechanical stress signals, leading to dysregulated collagen synthesis and bone matrix mineralization. Over decades of living in artificial rotation, shipborne humans develop altered bone trabecular architecture and microvascular remodeling that permanently alters their physical physiology. Furthermore, mechanical wear on central hub rotary seals creates a continuous environmental hazard. To connect spinning habitat rings to non-spinning propulsion and sensor modules, the vessel relies on high-pressure magnetic fluid seals and PTFE lip seals. Over billions of rotational cycles, mechanical friction and radiolytic breakdown degrade seal polymers, causing microscopic air leaks into space. Atmospheric makeup gas must be continuously supplied from onboard nitrogen and oxygen reserves to compensate for rotary seal leakage. If seal wear accelerates due to uncorrected precession wobbling, air loss rates surge, forcing the crew to ration atmospheric pressure or deploy high-risk in-flight seal replacement operations in zero gravity. Artificial gravity is thus a continuous operational tax that trades mechanical wear against human biological survival. In addition to biomechanical and mechanical joint fatigue, artificial rotation gravity introduces severe fluid dynamic anomalies inside human internal organs and cellular microenvironments. Inside the human inner ear, the semicircular canals rely on the movement of endolymph fluid against microscopic hair cells to sense head rotation. In a rotating habitat, moving the head out of the plane of rotation generates a Coriolis cross-coupling torque that drives endolymph fluid in directions inconsistent with visual perception. This neural sensory mismatch triggers severe autonomic dysfunction, chronic nausea, and spatial disorientation that can persist for months before partial neural adaptation occurs. However, every time a crew member moves from an outer 1G habitat deck to a central low-gravity utility hub, the brain must completely recalibrate its sensory motor mapping, causing chronic vestibular stress across decades of flight. Furthermore, continuous rotational acceleration alters cellular sedimentation dynamics inside human eggs and early embryos. During early embryonic cleavage, cellular organelles and maternal mRNA gradients rely on passive diffusion and subtle gravity-driven buoyancy currents to establish developmental body axes. In a rotating habitat with steep gravity gradients and Coriolis forces, embryonic cell division exhibits elevated rates of axial developmental defects, posing severe risks to multi-generational human reproduction. Moreover, artificial rotation gravity introduces complex mechanical resonance hazards in internal fluid distribution networks. In pressurized water lines running parallel to the deck rotation vector, fluid pressure surges caused by sudden valve closures known as hydraulic water hammer induce transient torsional shocks along structural spokes. These hydraulic shock waves interact with rotational Coriolis acceleration, creating high-frequency pressure oscillations that erode pipe elbows and damage pressure regulators. To suppress hydraulic shock waves, fluid systems must deploy heavy mechanical surge tanks and active dampening actuators throughout the spinning habitat volume. However, active dampening actuators consume auxiliary power and rely on sensitive piezoelectric pressure sensors that degrade under continuous radiation exposure. If a surge tank dampening valve fails, hydraulic water hammer shock waves propagate through load-bearing bulkheads, accelerating structural metal fatigue in internal deck frames. Additionally, artificial rotation gravity disrupts cellular membrane potential and ion channel gating kinetics in human nerve tissue. Voltage-gated sodium and potassium channels inside neuronal axons rely on microscale mechanical equilibrium within lipid bilayers. Under continuous rotational acceleration gradients, membrane lipid fluidity is altered, inducing subtle changes in nerve conduction velocity and action potential thresholds. Over decades of flight, shipborne humans experience altered peripheral nerve conduction speeds, manifesting as delayed reflex responses and subtle sensory paresthesias in upper and lower extremities. This neuromembrane alteration represents another layer of physiological adaptation enforced by mechanical rotation. While gravity management strains human physiology and mechanical structures, an even more insidious subatomic threat acts continuously on the traveler throughout the 1 light-year crossing galactic cosmic radiation. Outside the protective magnetic umbrella and atmospheric shield of Earth, which provides mass shielding equivalent to 10 meters of liquid water, the spacecraft cruises through an unattenuated storm of galactic cosmic rays, GCRs and solar particle events, SPEs. Galactic cosmic rays are ultra-high-energy atomic nuclei, mostly relativistic protons, helium nuclei, and fully ionized heavy elements like iron-56 originating from ancient supernova explosions across the galaxy. Traveling at near-light speeds with kinetic energies spanning giga-electron volts, these heavy HZE, high Z, and high-energy ions easily penetrate standard aluminum hull armors. When an HZE ion strikes a metallic bulkhead, it shatters target metal nuclei in a process known as nuclear spallation, generating a dense secondary radiation shower of fast neutrons, pi mesons, and gamma rays that pass directly through the crew's living quarters. Inside the human body, primary cosmic particles and secondary neutron showers cause severe cellular destruction. As relativistic heavy ions pass through living tissue, they leave behind dense ionization tracks, causing complex double-strand DNA breaks that overload cellular enzymatic repair mechanisms. Over a multi-decade crossing, cumulative radiation exposure leads to progressive DNA microdeletions, elevated lifetime risks of lethal cancers, accelerated cardiovascular tissue damage, and premature cataracts. Furthermore, cosmic radiation inflicts severe neurodegenerative damage on the human central nervous system. Relativistic heavy ions striking brain tissue cause neuroinflammation, synaptic loss, and destruction of neural progenitor cells in the hippocampus. Over years of transit, crew members experience cognitive decline, impaired memory consolidation, spatial disorientation, and altered executive decision-making. Shielding the crew requires thick hydrogen-rich materials such as polyethylene, liquid water bulkheads, or liquid hydrogen fuel tanks which add immense deadweight mass to the ship, creating a severe engineering trade-off between radiation protection and launch propellant budgets. Simultaneously, chronic low-dose radiation induces epigenetic dysregulation and accelerated telomere shortening in human tissues. High-energy particle strikes alter DNA methylation patterns across reproductive stem cells, passing mutational loads to offspring. Accelerated telomere attrition causes premature cellular senescence, early-onset cardiovascular disease, and reduced life expectancy in shipborne generations. In addition, radiation shielding material secondary activation creates ongoing internal radiation hazards. When heavy cosmic ions hit liquid hydrogen or water-shielding tanks, neutron capture reactions produce tritium and secondary gamma emitters, turning protective bulkheads into weak secondary radiation sources over multi-decade flight times. Moreover, cosmic particle strikes on neurochemical receptors inside the human brain alter neurotransmitter binding kinetics. Chronic exposure to secondary neutron showers reduces dopamine and serotonin receptor density, driving persistent emotional apathy, circadian sleep fragmentation, and impaired executive risk assessment capabilities in flight crews. Finally, high-energy particle radiation damages human mitochondrial DNA at rates far exceeding nuclear DNA damage. Mitochondria lack protective histone proteins, leaving their circular genome vulnerable to oxidative radiolytic stress. Over decades, mitochondrial decay causes cellular bioenergetic failure, chronic fatigue syndrome, and systemic organ dysfunction across the crew. To quantify radiation doses during a 1 light-year crossing, an unshielded astronaut in interstellar space absorbs approximately 0.6 to 1.0 sieverts per year. Over a 50-year journey, cumulative radiation dose reaches 30 to 50 sieverts, a dose hundreds of times higher than the career safety limit set for Earth astronauts, and far exceeding lethal single-exposure thresholds. Even with advanced active magnetic shielding deploying high-field superconducting coils to deflect charged particles, neutral cosmic rays and ultra-high-energy heavy ions above 10 giga-electron volts penetrate magnetic fields effortlessly. These ultra-energetic particles strike internal structural bulkheads, triggering dense secondary neutron cascades inside the habitat. Secondary neutrons are particularly destructive to biological tissue, possessing a radiation weighting factor up to 20 times higher than gamma rays. Furthermore, radiolytic decomposition of drinking water and hydroponic nutrient fluids produces toxic reactive oxygen species. ROS, such as hydroxyl radicals and hydrogen peroxide inside storage tanks. Drinking radiolytically contaminated water induces chronic intestinal dysbiosis, damaging gut mucosal lining and causing chronic systemic inflammation across generations. Subatomic radiation accumulation is the silent killer of interstellar flight. It cannot be felt, seen, or completely blocked by mechanical armor. Over light-year distances, radiation steadily degrades human genetics, neural wiring, and cellular energy systems, ensuring that those who reach the destination are biologically altered survivors. To understand the full subatomic threat of galactic cosmic rays, we must examine the biophysics of dense ionization tracks called HZE, tracks in human tissue. Unlike soft X-rays or gamma rays, which deposit energy evenly across tissue, heavy relativistic ions act like microscopic subatomic bullets. As an iron-56 nucleus traveling at near-light speed penetrates a human cell, it creates a dense core of primary and secondary ionization events that shatters both strands of the DNA double helix across multiple adjacent gene loci. These complex clustered DNA lesions are virtually impossible for cellular enzymatic repair mechanisms like homologous recombination HR or non-homologous end-joining NHEJ to repair accurately. Instead, cellular repair machinery frequently joins incorrect DNA ends, causing large-scale chromosomal inversions, translocations, and gene deletions. Over multi-decade spaceflight times, these cumulative genomic alterations drive somatic mutation rates to unprecedented levels, triggering early-onset leukemias, solid tumors, and tissue necrosis. Furthermore, heavy ion strikes destroy non-regenerative tissues in the human body, particularly central nervous system neurons and cardiac myocytes. When a heavy ion strikes a motor neuron or a cardiac pacemaker cell, the cell undergoes acute necrotic or apoptotic death. Unlike skin or liver cells, neurons and cardiac muscle cells cannot regenerate. Over decades of crossing, cumulative cell loss in the brain and heart leads to progressive cognitive impairment, loss of fine motor control, and premature cardiac failure across the crew. Radiation protection in deep space remains an unsolved biophysical problem. Passive shielding materials like water and polyethylene absorb lower energy particles, but ultra-high energy cosmic rays penetrate any practical shield thickness, generating secondary radiation cascades that can leave the internal environment more radiation hazardous than the open void outside. To examine the cellular impact of galactic cosmic rays in depth, consider the phenomenon of bystander effects in irradiated biological tissues. When a high-energy heavy ion penetrates a human organ, it directly strikes only a narrow track of cells along its path. However, damaged cells along the ionization track secrete stress-signaling molecules such as reactive oxygen species, cytokines, and microRNAs into surrounding unirradiated tissue through gap junctions. These signaling molecules induce double-strand DNA damage, chromosomal instability, and apoptosis in neighboring bystander cells that were never directly struck by the cosmic particle. This non-targeted radiation effect effectively multiplies the biological damage volume of a single heavy ion strike by a factor of 10 to 50, accelerating tissue degeneration across the brain, heart, and liver. Furthermore, space radiation exposure severely impairs human bone marrow stem cell niches, hematopoietic stem cells, HSCs, responsible for producing red blood cells, white blood cells, and platelets, suffer accumulated DNA damage that reduces their self-renewal capacity. Over decades of flight, crew members develop progressive space anemia, chronic lymphopenia, and impaired wound healing, leaving the body defenseless against internal injuries and opportunistic infections. Furthermore, chronic cosmic radiation exposure causes severe microvascular damage inside the human blood-brain barrier. Relativistic heavy ions and secondary neutron showers penetrating cranial tissues disrupt tight junction proteins in endothelial cells lining cerebral capillaries. This radiation-induced breakdown of blood-brain barrier integrity allows circulating inflammatory cytokines and neurotoxic metabolic byproducts to enter brain parenchyma. Inside the brain, neurovascular leakage triggers chronic neuroinflammation, accelerating microvascular dementia and astroglial scar formation. Shipborne humans living under unshielded galactic cosmic radiation experience progressive cognitive slowing, impaired spatial navigation skills, and early-onset neurodegenerative disease, severely compromising their long-term operational competence as flight maintainers. In addition, galactic cosmic ray strikes induce severe radiolytic degradation of internal medical supplies, pharmaceuticals, and synthetic biological reagents, complex organic molecules such as antibiotics, insulin, biological enzymes, and mRNA vaccines stored in medical bays undergo radiolytic bond cleaving under continuous secondary neutron showers. Over multi-decade flight times, life-saving pharmaceuticals lose molecular stability and bioactivity, transforming into inert or toxic chemical degradation products. Medical bays are forced to deploy high-energy chemical synthesis reactors to manufacture fresh pharmaceuticals on demand from basic elemental feedstocks, adding further energy and mechanical burdens to shipboard operations. Furthermore, continuous heavy ion bombardment causes radiolytic degradation of internal fluid purification filters, high-efficiency particulate air HEPA filters, activated carbon beds, and ceramic water distillation membranes absorb secondary neutron radiation, altering pore sizes and chemical adsorption capacities. Over multi-decade operational timelines, fluid filtration systems lose efficiency, allowing microscopic chemical contaminants, organic plasticizers, and heavy metal ions to recirculate through habitat drinking water and air loops. This progressive filtration breakdown subjects the crew to chronic chemical toxicities, compounding the cellular damage caused by direct cosmic radiation. Beyond physical material wear and subatomic radiation, a 1 light-year journey inflicts an intense, psychological sensory crisis on the human mind living inside an unchanging, isolated artificial enclosure for decades. On Earth, human psychology is continuously sustained by rich environmental variability, dynamic weather patterns, changing daylight spectra, seasonal shifts, natural landscapes, and diverse social interactions across millions of individuals. Inside an interstellar starship crossing the void, the sensory environment shrinks to a rigid, artificial baseline. The crew lives inside metal corridors illuminated by constant artificial LED spectra, breathing recycled air scrubbed of natural soil, volatile organics, and consuming synthetic or hydroponic food choices. The visual landscape ahead remains virtually unchanged for years, as distant target stars appear static despite travelling at thousands of kilometres per second. This sensory monotony induces profound psychological habituation, spatial claustrophobia, and chronic elevated cortisol stress levels. Furthermore, extreme social isolation creates severe interpersonal dynamics within small, closed crews, cut off from Earth by lightspeed communication delays spanning months or years. The crew cannot seek real-time psychological support, news updates, or social interactions outside the ship. Small interpersonal frictions, minor personality clashes, and subtle behavioral quirks amplify over time within enclosed volumes, leading to severe social polarization, groupthink, and institutional fracture. Prolonged sensory deprivation and social isolation also alter human circadian rhythms and neurochemical balance. The lack of natural solar blue light wavelengths disrupts melatonin synthesis and suprachiasmatic nucleus function, leading to chronic sleep fragmentation, clinical depression, and emotional blunting. The traveler crossing 1 light-year is not simply a pilot operating a vehicle. They become a psychological survivor navigating an internal mental abyss where the absolute silence of deep space threatens human sanity long before the vessel reaches its destination. In addition, microsocial cultural drift creates linguistic and institutional fragmentation over multi-decade voyages. Isolated human cohorts develop unique slang, altered idioms, and shifting social values. Original mission objectives established on Earth risk being reinterpreted through dogmatic group mythologies, where maintaining ship routine becomes a ritualized end in itself, rather than a means to reach a distant planetary destination. Moreover, psychological resilience is eroded by the absence of natural sensory feedback from living Earth biomes. The absence of natural soil scents, rain sounds, wind pressures, and animal life creates a chronic psychological deficit known as biophilic starvation. Crew members experience elevated baseline anxiety and emotional detachment, reducing their psychological capacity to cooperate effectively during complex mechanical or environmental emergencies. Furthermore, severe spatial confinement induces chronic neuroendocrine dysfunction, hypothalamic pituitary adrenal HPA axis. Dysregulation leads to elevated circulating cortisol levels, suppressing systemic immune function and impairing memory consolidation in crew members living under constant artificial lighting. Finally, sensory deprivation triggers profound existential despair known as the cosmic dread syndrome. Looking out into an infinite silent void, while knowing that Earth lies years behind and the destination lies decades ahead, induces severe psychological disorientation. Crew members struggle to maintain a sense of temporal continuity, leading to existential detachment, loss of personal agency, and psychological withdrawal. To analyze the psychological architecture of isolated environments, consider data from long-duration submarine deployments and polar research stations. In small, isolated cohorts, the third-quarter phenomenon frequently manifests a psychological condition occurring past the halfway mark of a mission, where motivation crashes, interpersonal conflicts surge, and adherence to safety protocols deteriorates. Inside a starship crossing a 1 light-year gulf, the third-quarter phenomenon is amplified by the impossibility of aborting the mission. Unlike a submarine that can surface or an Antarctic station that can be evacuated during polar summer, A starship cruising at relativistic speeds cannot turn around or stop mid-flight. The awareness of absolute confinement creates chronic existential helplessness. Furthermore, environmental auditory monotony presents an underestimated psychological hazard. Living continuously alongside the high-frequency hum of ventilation fans, coolant pumps, and electrical transformers causes auditory fatigue and chronic acoustic stress. The brain attempts to compensate for auditory sensory deprivation, leading to musical ear syndrome and auditory hallucinations among crew members during sleep cycles. The sensory void reveals that human psychology is not an isolated cognitive software that can run seamlessly in any environment. It is an ecologically embedded system that requires the complex, dynamic stimuli of a living planet to maintain long-term sanity. To explore the psychological impact of deep space isolation, consider the neurobiology of chronic stress and environmental deprivation. On Earth, human brain health is sustained by rich environmental novelty that stimulates neurogenesis in the hippocampus and maintains synaptic plasticity in the prefrontal cortex. Living inside a static, artificial metal habitat strips away environmental novelty, leading to hippocampal atrophy and prefrontal cortical thinning over time. This structural neural degradation manifests as impaired cognitive flexibility, reduced emotional regulation, and persistent executive dysfunction. Crew members become increasingly rigid in their thinking, less capable of adapting to unscripted technological anomalies, and prone to severe emotional blunting or explosive interpersonal conflict over minor domestic disputes. Furthermore, small group dynamics in extreme isolation follow predictable sociological degradation pathways. In closed human cohorts cut off from external society, informal social hierarchies form rapidly, often conflicting with formal command structures. Subgroups coalesce around shared grievances, creating factionalism and passive-aggressive non-cooperation that impairs ship maintenance discipline. During critical operational emergencies such as an atmospheric leak or a reactor cooling glitch, factionalized crews struggle to execute coordinated emergency protocols. Psychological breakdown inside an interstellar vessel is not simply an individual medical issue. It is a systemic mission hazard that can destroy a starship just as effectively as a hull puncture or engine failure. To explore the long-term sociological dynamics of deep space isolation, we must analyze the evolution of institutional governance models inside confined human habitats. On Earth, human societies rely on external judicial, economic, and political institutions to resolve conflicts and enforce social cohesion. Inside a starship crossing a 1 light-year void, social governance must be maintained within a tiny, closed population operating under zero-margin environmental constraints. Over decades of isolation, traditional democratic or consensus-based decision-making structures frequently break down under the stress of chronic resource rationing and operational risk management. The institutional structure tends to ossify into rigid, military hierarchical or technocratic regimes where individual autonomy is heavily restricted in favor of mission survival. However, this rigid institutionalization creates deep psychological friction between younger shipborne generations and older governing cohorts. Shipborne humans who never chose to board the vessel resist dogmatic operational mandates, leading to covert non-compliance, sabotage of environmental monitoring systems, and institutional paralysis during critical maintenance operations. Additionally, the psychological sensory void is exacerbated by the phenomenon of biophilic deprivation and olfactory habituation. On Earth, the human olfactory system is continuously stimulated by thousands of volatile organic compounds produced by soil microbes, ocean aerosol sprays, plant flora, and natural precipitation. Inside a closed starship, the air is continuously scrubbed by active charcoal filters and catalytic oxidizers, creating a sanitized, chemically flat olfactory environment. This chronic olfactory monotony leads to sensory habituation and anhedonia, the inability to experience pleasure from daily activities. crew members report a persistent sense of environmental numbness, leading to elevated appetite loss, chronic lethargy, and emotional detachment from shipboard duties. The absence of natural Earth sense acts as a silent psychological drain that erodes emotional resilience over multi-decade flight times. Furthermore, the psychological sensory void disrupts human dream architecture and sleep EEG patterns during long-term spaceflight. Polysomnographic studies in isolated habitats reveal a marked reduction in deep, slow-wave sleep (SWS) and rapid eye movement (REM) sleep stages, accompanied by frequent microarousals throughout the sleep cycle. This chronic sleep architecture fragmentation impairs memory consolidation, emotional processing, and neurotoxic waste clearance via the brain's glymphatic system. Over years of transit, crew members develop chronic neurocognitive fatigue, reduced attention spans, and elevated vulnerability to affective psychological disorders. Additionally, sensory monotony impairs social communication dynamics and group problem-solving capabilities. In small cohorts exposed to static environmental stimuli, conversations become repetitive, communication channels narrow, and novel ideas are met with institutional resistance or emotional irritability. This communication degradation compromises complex engineering problem-solving during operational anomalies. When automated systems signal unexpected component failures, crew members struggle to engage in open, creative troubleshooting, relying instead on rigid procedural checklists that fail to address novel failure modes. Furthermore, the psychological toll of long-duration isolation induces significant changes in interpersonal empathy and group decision-making dynamics. In small, confined cohorts, cut off from broader human society, social norms undergo severe contraction. Empathy fatigue sets in as crew members become habituated to each other's emotional states, leading to social withdrawal and emotional coldness during daily interactions. When complex operational crises occur, this emotional blunting inhibits effective teamwork and active listening. Factions within the crew become unwilling to compromise, holding dogmatically to divergent operational strategies. This breakdown in socio-emotional cohesion represents a critical mission vulnerability that can lead to catastrophic operational delays during life-threatening technical emergencies. Beyond kinetic hazards, radiation, and psychological isolation, a 1 light-year voyage demands managing an absolute thermodynamic mass-energy budget. Every megawatt of electrical power needed to illuminate agricultural crops, heat life support volumes, power computational arrays, and run artificial gravity rings must be generated from internal energy sources carried on board from launch. In the cold vacuum between stars, there are no external solar panels or energy fields to harvest. The vessel operates as an isolated thermodynamic system bound by the laws of nuclear physics and radiative cooling. To supply continuous gigawatt-scale power across decades, the spacecraft must rely on advanced nuclear fusion such as deuterium-helium-3 or deuterium-tritium fuel cycles or antimatter catalyzed propulsion systems. However, nuclear propellant carries physical mass, and that mass must itself be accelerated up to cruise velocity. According to Tsiolkovsky's rocket equation, carrying additional fuel to extend power grid operation exponentially increases initial launch mass, creating a brutal mass-energy feedback loop that limits operational lifespan. Furthermore, in thermodynamic waste heat management presents a severe physical barrier. According to the Stephen-Boltzmann law, waste heat generated by fusion reactors, life support systems, and computing grids can only be rejected into space via thermal radiation. Radiating gigawatts of low-grade waste heat requires massive, thin radiator panels spanning hundreds of thousands of square meters. These radiator arrays operate under constant risk of micrometeorite punctures and thermal fatigue. If primary radiator loops lose coolant fluid, internal habitat temperatures surge rapidly, forcing engineers to throttle back power reactors and reduce life support operations. The most critical energy debt occurs during the deceleration phase of the journey, To stop at a target star system 1 light-year away, the spacecraft must expend exactly as much propellant energy to decelerate as it did to accelerate during launch. If deceleration begins too late, or if fuel reserves bleed away through cryogenic leaks or unexpected operational consumption, the ship lacks the kinetic braking power required to capture into orbit around the target star. The vessel becomes a runaway interstellar tomb, doomed to shoot past its destination at thousands of kilometers per second into the infinite galactic void. Moreover, cryogenic fuel storage degradation presents an ongoing energy drain. Storage tanks holding liquid deuterium and helium-3 near absolute zero constantly fight thermal leakage from habitat decks. Cryocoolers can consume continuous auxiliary power to recycle refrigerant gases. Microgasket degradation and radiolytic embrittlement over decades allow heat leaks to penetrate fuel matrices, forcing automated relief valves to vent irreplaceable fusion fuel into space. Additionally, magnetohydrodynamic MHD energy conversion channels suffer high-temperature electrode erosion. As plasma flows through MHD channels to generate electricity directly without moving turbines, energetic ions sputter into metal electrode surfaces, reducing conversion efficiency and forcing reactors to burn higher fuel quantities per megawatt generated over multi-decade timelines. Furthermore, thermal stress cycles during mid-course maneuver burns create severe microcracking in main engine expansion nozzles. Radiative cooling skirts operating at thousands of degrees Celsius undergo rapid thermal contractions during engine shutdown, driving thermal fatigue along composite thrust chambers. Finally, power distribution buses suffer resistive energy losses and dielectric breakdown over decades of operation. High-voltage superconducting transmission cables lose critical cooling efficiency as cryocoolers degrade, forcing switching channels to operate under elevated electrical resistance that bleeds megawatt-scale waste heat directly into internal structural girders. To evaluate deceleration mechanics, consider the mass ratio equation for a two-stage relativistic burner, where V is effective exhaust velocity. For a vessel accelerating to 2% of light speed and then decelerating to orbital capture, the required fuel mass ratio scales exponentially with exhaust velocity. If fusion engines achieve an exhaust velocity of 5% of light speed, the ship must carry several times its payload mass in pure fusion fuel at launch. If fuel boil-off or micro-leakage reduces propellant inventory by even 5% during the multi-decade cruise phase, the vessel loses its capacity to execute a complete deceleration burn. The guidance software is forced to perform a partial braking burn, leaving the ship moving at several hundred kilometers per second relative to the target star too fast for gravitational capture. Furthermore, waste heat radiator panels face severe directional orientation constraints during deceleration. When the main fusion engines fire in reverse to slow the vessel, engine exhaust plumes emit gigawatts of thermal infrared and gamma radiation. Radiator panels mounted along the hull must be articulated away from the engine exhaust, while remaining oriented toward deep space, placing immense mechanical loads on rotary radiator positioning joints. The thermal and energy debt demonstrates that deep space is an unforgiving financial ledger governed by thermodynamics. Energy cannot be borrowed from the void. Every joule used to heat a corridor or break a hull must be accounted for from the moment of departure. To analyze the thermodynamic budget of a 1 light-year crossing, we must evaluate the efficiency limits of advanced thermonuclear fusion power systems. Deuterium-helium-3 fusion is often favored for interstellar flight because its primary reaction products are charged protons and alpha particles, which can be manipulated by magnetic fields for direct electrical conversion without intermediate steam turbines. However, deuterium-helium-3 fuel requires extreme ignition temperatures exceeding 600 million Kelvin, nearly 4 times higher than deuterium-tritium fusion. Achieving and maintaining these stellar temperatures inside a compact Starship reactor requires massive superconducting magnetic coils, high-power neutral beam injectors, and complex laser drivers that consume gigawatts of recirculating power. If recirculating power loops suffer efficiency losses due to magnet thermal degradation or power switching resistance, the reactor's net energy output crashes, threatening the entire ship's power grid. Furthermore, deceleration burn dynamics introduce severe propellant mass fractions. Decelerating a multi-thousand-ton vessel from 2% of light speed down to planetary capture velocity requires burning fusion fuel for months or years. As fuel is consumed during the braking burn, the ship's total mass decreases, altering its acceleration profile and center of gravity. Guidance computers must continuously recalculate thruster vectoring angles to prevent asymmetric thrust from tumbling the ship during high-power deceleration. If a single vectoring actuator jams or a magnetic nozzle coil fails during the braking burn, the vessel tumbles out of control, missing its target star system and hurtling helplessly into the dark void beyond. To evaluate the thermodynamic efficiency of deep space power systems, we must analyze magnetohydrodynamic MHD plasma channel degradation under continuous multi-gigawatt power extraction. In an advanced fusion power plant, ultra-hot plasma exiting the magnetic confinement core passes through MHD generator channels lined with high-temperature tungsten or rhenium electrodes. As high-density plasma flows through the transverse magnetic field at supersonic speeds, strong Hall currents develop along the channel walls. These Hall currents create localized arc discharges and thermal hotspots that erode electrode surfaces through electrical sputtering and thermal evaporation. Over decades of operation, electrode erosion widens channel gaps, reducing magnetic flux density and causing electrical power generation efficiency to drop by up to 20%. To compensate for dropping MHD efficiency, reactor controllers must burn higher quantities of precious fusion fuel, accelerating propellant depletion and threatening the ship's deceleration burn budget. Waste heat rejected by deteriorating MHD channels must be absorbed by internal cooling loops, further stressing primary radiator panels. Moreover, thermodynamic waste heat rejection during high-power deceleration burns is constrained by thermal radiation view factor limits. When main fusion engines operate at maximum thrust to slow the spacecraft, radiative cooling panels mounted on the rear hull are partially illuminated by hot engine exhaust plumes. This thermal illumination reduces the effective emissivity of radiator panels, preventing efficient waste heat rejection from reactor core heat exchangers. To maintain reactor cooling, flight engineers must deploy retractable thermal heat shields that shade radiator panels from engine exhaust. However, mechanical deployment linkages operating in high-temperature vacuum environments suffer from thermal expansion, binding and microweld friction. If a radiator shading shield fails to extend properly during deceleration, reactor core temperatures surge to emergency shutdown limits, forcing flight computers to abort the deceleration burn mid-transit. Additionally, thermonuclear fusion power grids suffer from magnetic containment coil quench hazards. Superconducting magnetic coils generating multi-Tesla magnetic fields to confine fusion plasma operate near critical cryogenic temperature limits. If a cosmic ray heavy ion deposits localized heat inside a superconducting cable, localized normal state quenching occurs. Magnetic quench triggers a rapid, catastrophic release of stored magnetic energy into liquid helium coolant loops, causing explosive helium boil-off and immediate shutdown of the primary fusion core. Emergency power switching grids must instantly divert auxiliary battery power to maintain critical habitat life support, while automated systems execute high-risk reactor reignition protocols. While energy reserves bleed away and radiation bombards the interior, a ninth physical force acts silently on every solid wall, girder, and seal onboard structural material entropy. On Earth, structural materials endure predictable mechanical loads and chemical weathering, but over a multi-decade crossing through deep space, structural alloys and composite materials undergo atomic scale lattice degradation, outgassing, and radiation embrittlement. Under continuous bombardment by galactic cosmic rays and secondary neutron showers, Metallic crystal lattices suffer from nuclear spallation and displacement cascades. High-energy particles dislodge target metal atoms from their fixed positions in the crystal matrix, creating microscopic Frenkel vacancies and interstitial dislocations, measured in displacements per atom dPa. Structural materials accumulate lattice voids that coalesce into submicron cracks. High-strength titanium alloys, carbon composites, and aluminum weaves lose ductility and fracture toughness, rendering load-bearing bulkheads brittle and prone to sudden shear failure. Simultaneously, high-energy neutron collisions trigger nuclear transmutation inside structural metals. Stable iron, titanium, and nickel atoms transmute into lighter radioactive isotopes and trapped helium and hydrogen gas. Microscopic helium bubbles collect along internal grain boundaries, acting as internal pressure wedges that separate metal grains and drastically reduce the material's fatigue limit. Over decades of continuous habitat pressurization and rotation, structural metal girders transmute into porous, gas-filled matrix structures incapable of holding design tension loads. In addition, materials exposed to space vacuum suffer from outgassing and radiolytic polymer degradation. Volatile plasticizers, synthetic lubricants, and organic sealants slowly evaporate into the vacuum of space, causing rubber gaskets and electrical wiring insulation to become brittle and crumbly. Microcracks develop in unpressurized conduit seals, leaking atmospheric gases into structural wall cavities and causing electrical short circuits in automated control channels. Furthermore, radiation-induced segregation RS along alloy grain boundaries accelerates intergranular stress corrosion cracking. Solute atoms like chromium and nickel diffuse away from grain boundaries under neutron bombardment, destroying chemical uniformity. Even trace atmospheric moisture inside pressurized habitat modules interacts with these chemically altered grain boundaries, triggering intergranular micro-cracks under normal operational loads. Moreover, anisotropic lattice expansion causes structural girders to bow unevenly over flight time. Non-uniform thermal expansion combined with radiation-induced lattice distortion introduces parasitic shear stresses across primary deck bulkheads, accelerating microcrack propagation along welded structural seams. Additionally, outgassing of volatile organic plasticizers from electrical insulation degrades signal transmission speeds in fiber optic data channels. Microvoids forming inside fiber optic cores cause optical attenuation, leading to silent data corruption in flight control computing grids. Finally, thermal fatigue in multi-layer insulation MLI blankets destroys passive thermal protection. Exposed to continuous solar ultraviolet radiation during launch and high-energy cosmic rays in deep space, MLI aluminized mylar sheets embrittle and flake away, creating thermal cold spots across external pressure bulkheads. To examine atomic dislocation dynamics in detail, consider the accumulation of Wigner energy in irradiated graphite and composite structures. When fast neutrons knock atoms out of their equilibrium lattice positions, potential energy is stored in the distorted crystal matrix as Wigner energy. Over decades of continuous exposure, Wigner energy accumulates within structural bulkheads. If a localized thermal pulse occurs, such as a minor thruster firing, or an electrical short circuit, the stored Wigner energy can release spontaneously in an exothermic thermal surge. This sudden energy release causes localized thermal spikes exceeding thousands of degrees Celsius, triggering thermal shock fractures along primary load girders. Furthermore, outgassing in vacuum leads to cold welding between unlubricated metallic surfaces. In non-pressurized utility channels where solid lubricants have evaporated or flaked away, clean metal components in contact with one another bond atomically under mechanical pressure. Actuator valves, mechanical latches, and emergency hatches weld permanently shut, preventing automated maintenance droids or crew members from operating critical utility controls. Structural entropy reveals that a starship is not a permanent metallic sanctuary, but a decaying physical skeleton. From the moment of departure, Every atom in the hull is engaged in a continuous descent toward disorder, setting a hard physical expiration date on the mechanical integrity of the vessel. To examine structural material entropy at the atomic level, we must consider the phenomenon of radiation-enhanced creep and phase instability in metal alloys under continuous high-energy particle bombardment and elevated mechanical stress. Atoms in structural metals undergo accelerated diffusion rates, allowing metal crystals to deform permanently at temperatures far below their normal thermal creep threshold. Primary load-bearing girders made of advanced titanium or nickel alloys slowly stretch and warp under constant artificial gravity tension forces. Over multi-decade flight times, structural bulkheads bow by several centimeters, introducing parasitic shear stresses into adjacent deck joints and pressure seals. Structural alignment tolerances engineered to sub-micron precision drift out of specification, causing mechanical actuators, cargo hatches, and docking seals to bind or jam. Furthermore, atomic outgassing in vacuum causes severe degradation of optical coatings and thermal emissivity surfaces. Volatile elements contained in structural polymers, adhesives, and electrical insulation slowly evaporate into space, redepositing as thin organic films on nearby cold surfaces such as optical camera lenses, star tracker viewports, and thermal radiator panels. This organic film contamination darkens optical lenses and reduces the infrared emissivity of radiator panels, causing internal heat to accumulate inside habitat decks. Structural material entropy is an invisible, continuous process that systematically degrades every mechanical, optical, and electrical component aboard the vessel. To examine structural material degradation at the atomic scale, consider the phenomenon of helium embrittlement and void swelling in face-centered cubic FCC and body-centered cubic BCC metallic lattices. Under continuous neutron bombardment, alpha particles and recoil metal nuclei trapped inside structural girders generate helium gas atoms through N-ELPA nuclear reactions. Because helium is completely insoluble in solid metals, trapped helium atoms rapidly diffuse to high-energy sites like grain boundaries, dislocation loops, and microscopic vacancies. As helium atoms cluster together, they form high-pressure microscopic bubbles that exert internal pressures measured in gigapascals against surrounding metal grains. Under continuous mechanical loads from artificial rotation, gravity, and habitat atmospheric pressure, these microscopic helium bubbles act as stress concentrators, promoting intergranular microvoid coalescence. Structural bulkheads suffer severe loss of tensile ductility and impact toughness, transforming high-strength aerospace alloys into brittle, porous matrices prone to sudden macro-cracking under normal operational loads. Furthermore, structural material entropy is intensified by the phenomenon of radiation-induced void swelling in high-strength composite materials. In carbon fiber reinforced polymer CFRP girders used for secondary habitat framing, high-energy neutron bombardment breaks carbon-carbon polymer bonds, creating microscopic gas microvoids within the resin matrix. Over decades of spaceflight, these microvoids expand under internal habitat pressurization, causing structural composite beams to swell, warp, and lose flexural stiffness. Structural joints connecting composite frames to metallic hull bulkheads experience severe thermal expansion mismatches, generating high shear stresses that cause joint delamination and atmospheric microleaks into unpressurized structural cavities. Moreover, structural material entropy is compounded by radiolytic embrittlement of fiber optic data transmission buses. Multi-gigabit data networks running through unpressurized utility channels rely on high-purity silica glass optical fibers to route flight control telemetry and automated sensor signals throughout the vessel. Under continuous cosmic particle radiation, color centers and electron hole traps form inside the silica glass matrix, causing progressive optical darkening and signal attenuation. Over decades of transit, data transmission error rates spike across primary computing buses, forcing control systems to drop transmission speeds or replace thousands of meters of degraded optical fiber in hard-to-reach structural channels. Moreover, structural material entropy leads to progressive metrology decay across secondary maintenance workshops. Physical calibration gauges, laser interferometers, and micrometer standards stored in utility bays undergo microscopic atomic displacement and thermal expansion over decades of spaceflight. As primary measurement standards drift, spare parts machined by flight maintainers suffer from cumulative dimensional tolerances. Replacement valves, pressure seals, and bearing sleeves produced late in the mission fail to fit structural housings precisely, leading to microleaks, mechanical play, and accelerated vibration wear throughout mechanical systems. In addition, radiolytic cleavage of polymeric structural adhesives destabilizes internal composite joints and equipment mountings. Structural adhesives used to bond internal deck bulkheads, vibration dampeners, and sensor brackets to the outer hull suffer from progressive molecular bond scission under continuous secondary gamma-ray and neutron irradiation. Over multi-decade flight times, adhesive bonds lose shear strength and become brittle. Internal machinery mountings loosen, introducing high-amplitude vibration chatter during main engine firings and attitude control maneuvers. This mechanical chatter accelerates joint wear and creates secondary acoustic noise hazards throughout human living quarters. When we synthesize all physical, biological, ecological, and sociological limits explored across this journey, a profound revelation emerges. Crossing 1 light year is not simply a journey taken by human beings inside a machine. It is an evolutionary crucible that permanently transforms the traveler. The humans who arrive at the 1 light year mark are not physically, genetically, or culturally identical to the humans who launched from Earth decades earlier. Biologically, multi-decade exposure to low-dose cosmic radiation, artificial rotation gravity, synthetic diets, and degraded microbiomes alters human physiology at a foundational level. The travelers possess altered immune responses, elevated genetic mutation burdens, reduced bone density baseline, and altered cardiovascular mechanics. If children are born during the voyage, they represent a new subspecies of humanity, adapted to artificial light, steel corridors, and enclosed atmospheric loops, knowing Earth only as an abstract historical legend recorded in digital archives. Sociologically and culturally, the isolated crew undergoes profound institutional evolution. Cut off from Earth by 2-year light travel communication latencies, the travelers develop independent social structures, unique linguistic dialects, and altered ethical frameworks. The original Earth-based mission priorities succumb to the immediate imperatives of shipboard survival. The spacecraft transforms from a transport vehicle into a self-contained, dogmatic habitat, where maintenance routines assume sacred cultural significance. Furthermore, the existential realization of crossing a 1 light-year void fundamentally alters human philosophy and cosmology. Having experienced the complete detachment from Earth and survived the relentless thermodynamic trial of deep space, the travelers view themselves not as colonists visiting another star, but as a permanent technological diaspora. Their relationship with technology, nature, and time itself is irrevocably altered. Ultimately, a 1 light-year crossing delivers a sobering lesson regarding humanity's place in the cosmos. Interstellar space is not a friendly vacuum easily conquered by mechanical ambition. It is an unyielding thermodynamic barrier that enforces strict limits on biological life. An interstellar starship is not a permanent replacement for a planet, but a consumable, high-risk technological bridge across the cosmic dark. Understanding the hard physical realities of a 1 light-year journey deepens our reverence for Earth's unique planetary engine. Every breath of air we take on Earth is passively filtered by oceans and forests without machinery. Every cell in our bodies is anchored by a gravitational field that never suffers mechanical wear, and our atmosphere provides passive magnetic and physical radiation shielding that no spacecraft can match. As humanity looks toward the stars, our journey across the light years begins not with abandoning our home world, but with recognizing that our ultimate destiny depends on finding, reaching, and cherishing real planetary worlds capable of sustaining life for eternity. To reflect on this transformation, consider the physiological divergence of ship-borne offspring. Generations born under artificial rotation, gravity, and cosmic radiation develop altered skeletal proportions, modified cardiovascular pressure regulations, and unique metabolic pathways optimized for synthetic food slurries. They are physically incapable of surviving on Earth without extensive medical adaptation, just as Earth-born humans struggle to survive inside the starship. Culturally, the concept of home undergoes a total paradigm shift. For Earth-born pioneers, home was a world of blue skies, oceans, and natural biomes. For shipborne generations, home is a 1,000-meter steel cylinder surrounded by absolute vacuum, where survival depends on unyielding adherence to recycling protocols and reactor maintenance routines. Earth is no longer a physical place to return to, but a mythical ancestral origin story. In the final analysis, crossing 1 light-year teaches humanity its most profound cosmological lesson. Technology can extend our reach across the cosmic dark and build specialized bridges between stars, but it cannot free us from our biological and thermodynamic dependence on planetary worlds. We do not leave Earth to live forever inside machines. We cross the void in search of new planetary hearths, where life can bloom once more under a real star. When we synthesize all physical, biological, ecological, and sociological dimensions of a 1 light-year journey, we arrive at a profound cosmological conclusion. Interstellar space is a fundamental biological filter. It is an unyielding thermodynamic barrier that separates star systems, ensuring that only species capable of mastering extreme physics, bioengineering, and sociological discipline can cross the cosmic gulf. The humans who successfully cross 1 light-year are no longer Earth-dwelling organisms. They have evolved into a spacefaring species whose physical biology, psychological architecture, and cultural values are permanently anchored to the technological environment of the starship. They carry Earth's genetic memory in their DNA, but their lived reality belongs entirely to the void between stars. Ultimately, the journey across 1 light-year reshapes our understanding of human destiny. It teaches us that leaving our home planet is not a casual technological expansion, but a profound evolutionary transformation. The starship is a consumable bridge across the dark, and its true purpose is to carry the fragile flame of terrestrial life across light years of void until it can find a new planetary hearth to call home. As we look toward the stars, the hard physics of interstellar flight reminds us of the extraordinary rarity and value of Earth. Our planet is an ancient, self-regulating biological sanctuary built over 4.5 billion years of coevolution between geology, atmosphere, and life. To cross the light years is to honor that origin, carrying the ember of the Earth's life across the cosmic dark to ensure that consciousness continues among the stars. To synthesize the ultimate biological and cosmological transformation of the traveler, consider the long-term evolutionary trajectory of humanity beyond Earth. A 1 light-year crossing is not merely a technical mission executed by an existing species. It is the speciation horizon of Homo sapiens. Living under artificial rotation gravity, exposed to chronic low-dose cosmic radiation, eating processed synthetic nutrient slurries, and isolated from terrestrial environmental microbes, human biology undergoes rapid physiological and genetic divergence. Within a few generations, natural selection and genetic drift fix novel mutational adaptations such as altered bone mineralization pathways, modified vascular pressure regulation, and enhanced cellular DNA repair enzymes. These shipborne humans are no longer terrestrial organisms temporarily visiting space. They have evolved into obligate technological organisms whose physical biology is permanently linked to the life support architecture of the starship. Returning to Earth would be fatal to them, just as sending unadapted Earth humans into deep space is fatal without massive technological shielding. Crossing 1 light-year demonstrates that humanity's future among the stars will not be written by Earthborn humans preserving their ancestral biology, but by a new, transformed lineage born of the cosmic void, carrying the fire of terrestrial consciousness across the light years to seed new planetary worlds. Ultimately, the transformed traveller represents a profound evolutionary paradigm shift for human civilization. A 1 light-year journey demonstrates that space exploration is not an external mechanical activity, where human beings will remain unchanged while moving across spatial coordinates. It is an intimate co-evolutionary process where technology and biology adapt to survive in extreme physical environments. The humans who arrive at a distant star system carry the torch of Earth's cognitive legacy, but they are no longer children of Earth's biosphere. They have become an interstellar species Homo spacium, whose physical architecture, psychological orientation, and social culture are permanently forged in the crucible of deep space. Their journey teaches us that our ultimate destiny among the stars lies not in preserving our past, but in embracing the profound transformations required to inhabit the cosmos. In the final analysis, reaching the 1 light-year horizon represents humanity's ultimate triumph over thermodynamic entropy and physical isolation. It is a monument to the power of scientific reasoning, engineering rigor, and psychological resilience that a biological species born in Earth's gentle cradle can build a vessel capable of crossing the cosmic abyss. As the starship approaches its destination star system, the transformed crew prepares to enter a new planetary cradle. They carry with them the physical scars, biological adaptations, and cultural wisdom forged across light years of void. Their epic crossing proves that while planets are the essential cradles of life, the human spirit possesses the capacity to bridge the stars, turning the cold void of space into a pathway for the eternal expansion of terrestrial consciousness. Furthermore, the philosophical legacy of a 1 light-year journey permanently reframes human self-conception within the cosmic order. Moving beyond the gravitational and biological protection of Earth forces, the traveller to confront the absolute indifference of deep space, shattering anthropocentric mythologies and replacing them with a stark, thermodynamic realism. This philosophical shift elevates technological stewardship into a fundamental moral imperative. Maintenance of life support loops, reactor containment, and radiation shielding is no longer viewed as mere technical labor, but as the sacred preservation of terrestrial consciousness within an unyielding void. The transformed traveller becomes a living guardian of life's fragile ember, carrying it across the dark toward a new planetary home.